Hi, welcome to this new session, Hadoop. In this session, we are going to touch one of the most important components of Hadoop, that is MapReduce, and we'll face with the architecture of MapReduce in the Hadoop context, and also the usage of MapReduce approach for parallel computing in data mining. Indeed, so we'll face with the Hadoop environment with a quick recap of what we have done in the previous session. And we'll go through a quick list of some common applications of the MapReduce programming paradigm. After that, we'll go in depth in the paradigm of MapReduce in parallel programming. I will make a quick comparison of the early version of Hadoop and Hadoop Yarn. That is a new version called also MapReduce 2.0. And we'll conclude our discussion with quiz, examples, and exercise. So let's start with the Hadoop environment that we faced in the last session on Hadoop. We have seen that Hadoop is made by four main components, four main areas in the architecture. We have the Hadoop binaries, the data storage that most of the times is based on the HDFS, the file system of Hadoop, but it can go also on the cloud. And in this case, we have seen that there are a trade-off between the cost of communication on the cloud and the usage of the local resources with HDFS. Today we touch MapReduce, and we have seen that it is also possible to have additional libraries that can extend the functionalities of Hadoop. So common applications of MapReduce is very popular, and we use it every day. If you think about Amazon, Google, and Yahoo, they use MapReduce parallel programming for the indexing of the search. So when we make a search, we use MapReduce. Indeed, the MapReduce is used in text mining, index building, graphs, but also in machine learning. Prediction is a very popular topic for MapReduce, and it extends its functionalities until up to the risk analysis, so the fraud detection, etc. The MapReduce workflow is very simple. The parallel programming approach the analysis of big data, splitting the data to be analyzed in chunks. Like here you can see the chunks that are coming in input. It is a data flow. The data flow analyzes from the left to the right the data that comes in the MapReduce component and produce an output at the end. So when the data comes in, you can see we have here different blocks of data, and we'll see later how these blocks are created. They pass through a first step made by map functions that actually map the function, map the data based on an internal business logic the developer has to produce, and produce as output a list of values. These values are in the form of key values, so they are a list of pairs, and in this context these are called tuples. So the tuples here are ordered, for example, by color. This is what the intermediate function shuffle prepare the data before the last step in the MapReduce workflow, and once this is done, they are sent to one or many nodes. At the end, what we have is a list of tuples, also in this case, that are produced by the reduce function, and the reduce function normally take the input data that are tuples and aggregates or binds, join, elaborate the data sets in input to produce as a list of output. We know very well some reduce functions, for example, the sum. Often we use these functions also, for example, when we have data sheets in Excel. When we have a table, we want to create a sum of values or we want to aggregate data. There are a lot of functions in Excel that can do that. MapReduce want to create this data flow and produce at the end an output that can be used by the developers or by the data consumers. So once they produce the list of tuples, they are in some way aggregated towards the output. This is done always by the MapReduce component. So all these arrows are communications among nodes. All of these circles here are functions that could reside in different computers. So we could have in this context 7 data nodes. Each one will be responsible for the execution of a MapReduce function. And you can see here that the data are elaborated in parallel. In this diagram, it's possible to go more in depth. We have seen several data nodes in the MapReduce data flow. And in this timeline, we can see the main task that we have in this example. So first of all, data blocks are entering in the MapReduce component, and these are formatted using an important aspect of Hadoop. And we have seen that the file system of Hadoop is made by blocks. So the data are stored in blocks, and we have seen that normally one data is 64 megabytes. Hadoop normally follows the same approach for managing, for elaborate this data, and it uses to transform data blocks in input splits. These input splits that you see here are blocks of 64 megabytes that Hadoop MapReduce can elaborate in sequential in this case, because the map function that you see here that elaborates these input splits work in parallel and in sequential mode. So all the data come here, elaborated record by record in sequential, and they produce, the output produced is a list of key values. And the first operation we can do with the key values are in the preparation of the blocks for the reduce function here. So when we are here, actually we do not work on the data set, but on the single records. Instead, when the output is produced, here we can play with a bunch of data blocks. They can be combined, ordered, shifted, or whatever is important for the reduce function, and sent to the function reduce. The reduce function takes always the same pairs as input. We have always pairs, key, list of values. So we could have K2 and here a list of values, V1, V2, V3, and so on. So the reduce function produces the output, and the output is sent at the end to a MapReduce component that merge or in case save in the HDFS or in the cloud the results of the elaboration. Here you can see a quick notation on the different steps. We have seen that from the mapper we shuffle or sort the intermediate level of data, we copy the output to some reducer task, we make the reduced task, we write the result, and we replicate the result. Here we have the main components with the data passed. We have the map function that has as input k1 v1, and the output is a list of key values that are the input of the reduced list. The reduced list accepts for each key all the outputs coming from all the mapping for that key. That is why we have a list of keys. And the output is a list of pairs of these tuples. So let's have a look quickly on the architecture. It's not fundamental for the MapReduce paradigm that we have seen, but it is important in terms of implementation of MapReduce parallel programming applications. In the early version of Hadoop, we have seen the main components are the file system called Hadoop distributed file system that stores the data across a cluster of computers, and it also manages redundancies, backup, recovery, etc. And we have this big component, Hadoop MapReduce, that not only provides the parallel programming model, but it also manages all the resources, all the scheduling, all the parallel components that are involved in this elaboration. So it means that it manages the physical resources, sending the data, preparing the data, analyzing what is the situation of all different nodes during the elaboration of MapReduce, and distribute computation over the cluster. So if a cluster is overloaded, then the MapReduce component can send the data to be elaborated to another computer, to another data node that can make the same thing, and also provide the status reporting and monitoring. So here we have the merger of the parallel programming functions and the resource of the component. But this has changed, because in the new version of Hadoop, the part related to the management of the resources have been decoupled, detached. So we have here the Hadoop distributed file system, it remains as it is, and we have a new Hadoop MapReduce that provides the parallel programming model and allows the developers to input, to prepare scripts and languages for the MapReduce. But all the components, the resources for the management of nodes and application in the MapReduce are demanded to a new component. And you can see online that it's possible to go in depth in the architecture of the system, more in depth. So let's start with the first quiz. I'm asking you which stage of MapReduce has the worst complexity execution? The split, the map, the combine, or all of the above? Here we're talking about the complexity executions in terms of cycles in the processor to elaborate data, or complexity in terms of workload of the system when we have to elaborate one of these steps, or even when we have to communicate the data among two or more data nodes. So the answer is, well, it depends. This is because everything depends on how we create the algorithm to implement the MapReduce functions. So my suggestions on this is choose a good trade-off between the computation and the communication cost. We have seen that if we have as a file system the cloud, the problem of this solution is the communication. We have to send every time the data through internet, and this could have some delay in the elaboration of the data. if we have the HDFS installed locally, then we have to make sure to have good resources in terms of hardware capacity of the system to elaborate the data. And this could have a cost. Another important aspect is the complexity of mapping, shuffle, sorting, and reducing that can vary depending on the configuration and the algorithm. Here we're talking about the configuration of Hadoop as architecture per se. We are talking about the configuration files. We are talking about the algorithm and how the architecture is called. So the primitives of the elaborations are used to make the MapReduce work. So the first practical example of Hadoop MapReduce, of the MapReduce component is the word count problem. How can we create a MapReduce algorithm that can find the frequency of each word in the document? So we want to develop a MapReduce schema for an application that takes text as input and returns the number of words contained in the text. The example, if we have an input text like Matteo and Viola play together, Matteo did play on the beach and Viola did not play, we want to have the output from MapReduce component based on the occurrences of each word in the document. So for example, we have here as output Matteo and 2 as a first tuple output of the component, and we have seen Matteo is indeed used twice in the input text. Then we have another tuple and 2. It means that the word hand is used twice in this input text. The same for Viola 2, play 3, together 1, did 2, etc. How can we implement this in the Hadoop paradigm? It's very simple. You can see here that the overall MapReduce word count process is defined with the same phases that we have seen before. So if this is the input document here, we first split by carriage return the input text in multiple text. And then we call these input splits. And then we send them to data nodes for the mapping operations. The mapping operations simply calculate for each sentence the occurrence of each word in the sentence. So for the word deer, here we have only one, beer 1, river 1. Good, so once we have all of these ready, we have an intermediate process that prepares the data for the reduce. And here we simply sort by the first value, that is the key. So we send then, in the mapping, we send the output to each shuffle node that elaborates that word. Once we have this, we send all of these values to reducing functions, and then we aggregate these values with the sum of the values. So we have here beer 2, cat 3, deer 2, river 2. These are the occurrence of the word, of the key, of the tuple. At the end, we simply join all the output coming from the reduce function, and we release the output to the user, to the developer. So let's have a very practical exercise. What I'm asking you to prepare is a diagram that finds the mean of the hourly precipitation in USA in 2012. So how many centimeters, millimeters of rains we had in the USA in 2012? You can download the datasets, very simple datasets here, and you can play with the numbers to create at the end a very simple MapReduce workflow. You can download the solution on our homepage of the course. So let's have another quiz. So based on the input that you collected so far, what is the programming language supported by MapReduce? Number one, the most common programming language is Java, but scripted languages are also supported via Hadoop streaming. Two, any programming language that can comply with MapReduce. Three, only Java supported since Hadoop has been written in Java. Four, currently MapReduce supports Java, C, C++. So what is the right answer? So this is the answer. The most common programming language is Java, and we have seen also in the previous session on Hadoop. But all scripted languages can be supported via Hadoop streaming. We have PHP, Python, Perl, Ruby, Bash, JavaScript, R, and even there is a SAS module for the SAS scripting. Another exercise that I want to produce, is how can we implement the k-means clustering algorithm in MapReduce. So consider a set of points with a cluster centroid to be set in a runtime. I'm asking you list the main operations to reproduce the k-means clustering algorithm using the MapReduce paradigm. Here on the right side you can have a very quick example of the algorithm for the k-means clustering. What I'm asking you is to produce this MapReduce cloud that has as input some points, the MapReduce defines the cluster centroids, so it's up to you to decide how you want to start with the centroids, and a producer as output a clustering. I want to give you a very quick solution that you can find online, but I invite you to experiment on your own how to create the paradigm, MapReduce paradigm using this algorithm. Here we have a solution, very simple. We have the partitions as input. The mappers compute k-clusters for each partition. Centroids are calculated. And the reducer merges centroids for the partitions to global centroids. And this is a loop that is done until you cluster all your points. There is also a Java implementation you can find online. This is the address. So we are closing this session now. What we touched there, so we introduced the MapReduce as a paradigm and component. It greatly simplifies writing large-scale distributed applications, very powerful. It is widely used for large-scale machine learning and data mining applications. Early version of Hadoop MapReduce included also resource management functionalities, and today no more. So the new version of Hadoop can even replace the MapReduce with another parallel programming approach and use always Hadoop as architecture. So you can see online several examples and text on Hadoop. You can of course contact me via email or via mobile during this period, and thank you.